Welcome to this explainer. Okay, let's dive right in, because today we are dissecting a genuinely fascinating paper. It takes on a massive challenge, bridging the gap between abstract deep learning research and real life-or-death clinical deployment. We're looking at a highly reliable, scalable triage system for lung cancer called OncoTriage. Now, if you've been following clinical AI at all, you know that building a model that just crushes it in a lab, well, that's really only half the battle. The true test is deploying an architecture that can handle uncertainty safely, especially inside a resource-constrained hospital. So consider this explainer part top-tier conference talk, part clinical deployment pitch. We are going to focus heavily on how we actually transition from just having high accuracy to building genuine trustworthiness. Here is our roadmap for today. We'll quickly cover the oncological triage crisis, the problem with deterministic AI, the uncertainty-aware clinical architecture, our performance and calibration results, scalability and real-world deployment, and finally, building trustworthy clinical AI. All right, kicking things off with Section 1, the oncological triage crisis. We're looking at the global burden and diagnostic bottlenecks. Lung cancer is absolutely devastating. It's the leading cause of cancer-related mortality worldwide. But to really ground this abstract math in reality, we need to look at the Colombian healthcare system, which is exactly what this research contextualizes. In Colombia, the 5-year survival rate for lung cancer is a staggering 17%. It's one of the absolute lowest in the Americas. Why? Late-stage diagnosis. Low-dose CT screening does work, but in medium complexity hospitals, it gets severely bottlenecked. There simply aren't enough specialist radiologists around to interpret these high volumes of CT scans in near real time. And this perfectly highlights a huge tension in the field. Over 95% of pulmonary nodules detected in screening populations are completely benign. But as it stands, a human expert literally has to look at almost all of them just to find the rare malignancies. It's a needle in a haystack problem that creates a crushing review burden. The missing link here isn't just buying a better CT scanner, it's building a scalable triage system. We desperately need an intelligent layer to stratify these nodules fast and securely route only the ambiguous cases to those scarce specialists. Moving right along to Section 2, the problem with deterministic AI, or the danger of overconfidence. Now, you might be thinking, wait, don't we already have deep learning models that can detect these nodules? And we do. But standard convolutional classifiers have a fatal flaw in medical imaging. They are deterministic. They spit out point estimates without actually quantifying how confident they are. Essentially, they can be confidently wrong. And in medicine, there's no way around it. That is incredibly dangerous. Contrast that with Bayesian deep learning using Monte Carlo dropout, or MC dropout. By running multiple stochastic forward passes, it generates predictive distributions. It captures what we call epistemic uncertainty, which basically means the model actually knows when it doesn't know something. In a clinical setting, uncertainty quantification is not a bug. It is a vital safety feature that triggers a safe fallback to a human. Which leads us perfectly into Section 3, our uncertainty-aware clinical architecture, specifically focusing on EfficientNet B4 and the triage pipeline. What's truly innovative about this paper is how the researchers treat hospital capacity. They don't just see it as an IT problem, they treat it as a rigorous mathematical problem using queuing theory. They introduce the diagnostic throughput functional. This is a first-order ordinary differential equation framework that mathematically proves how your AI architecture choice directly impacts hospital processing capacity. It balances empirical accuracy, gradient sensitivity, and logarithmic pre-processing amortization. The short version? A more accurate model might take a fraction of a second longer per image, but if it drastically reduces the number of cases a human has to double-check, overall hospital throughput goes way, way up. So let's walk through how this actually flows in practice with the OncoTriage v2.1 system architecture. A clinician uploads a batch of CTs through a web interface. The fast API server, which runs the EfficientNet B4 model with MC dropout, gets to work. But watch the flow of information. The predictions in spatial heat maps don't just sit in a database. They directly drive an intelligent routing decision. If the model detects high epistemic uncertainty, boom, the case is automatically routed to a radiologist for manual validation. And the best part? Those human-validated cases feed right back into a retraining pipeline via active learning. It's this beautiful, continuous loop of improvement. Okay, let's get into the hard data in Section 4, performance and calibration results, looking at empirical proof and state-of-the-art benchmarks. The performance leap here is phenomenal. When benchmarked against domain state-of-the-art models like Luna 16 and ChecksNet, the results speak for themselves. The older deterministic ResNet 50 hits an AUC ROC of about 0.95. Adding MC dropout to ResNet bumps that to 0.97, but the proposed EfficientNet B4 with MC dropout, it absolutely leaps to a 0.99 AUC ROC. This is largely thanks to compound scaling, where the network's depth, width, and resolution are scaled simultaneously. It picks up incredibly subtle features for nodule discrimination, and amazingly, it does this using about 25% fewer parameters than the ResNet 50 baseline. But raw accuracy is only part of the story. Calibration is the real game changer. Expected calibration error, or ECE, measures how closely the model's confidence matches its actual accuracy. This architecture slashes ECE from 0.074 down to a remarkable 0.024. That is a 68% overall calibration improvement. Operationally, that means if this system says it's 95% confident, you can actually trust that it's 95% confident. The mean epistemic uncertainty is lower too, meaning the system only has to route 5.8% of cases for mandatory human review. That drastically cuts down radiologists' workload while maintaining an incredibly strict safety net. This naturally brings up a super important clinical reality that's actually baked right into the system's loss function. You might ask, why penalize false negatives 10 times more heavily than false positives? Well, in oncological screening, context is literally everything. If the AI flags a benign nodule as suspicious, a false positive, sure, it slightly increases the radiologist's review burden for a few minutes, but if it misses a malignant nodule entirely, a false negative, that patient might go undiagnosed until the cancer reaches a fatal stage. The triage thresholds are mathematically forced to catch uncertainty precisely to prevent those devastating false negatives. So, how do we actually put this into practice? Let's hit Section 5, Scalability and Real-World Deployment. We are taking this from the lab straight to the hospital infrastructure. Medical AI is notorious for breaking down when it moves from a pristine dataset in a lab to a real hospital. We call this distribution shift. You're suddenly dealing with different scanner brands, weird noise profiles, motion blur, and Hounsfield unit variations. To combat this, OncoTriage utilizes an active, continual learning loop. When a new hospital's data causes a spike in the model's uncertainty, it safely falls back, pinging the radiologist to review those tricky cases. That radiologist's validation is then absorbed back into the system to retrain the model weights, so the AI is literally adapting to the unique population dynamics of whatever hospital it's deployed in. And deployment isn't just a software problem. You're dealing with strict hardware and regulatory realities. The researchers stress-tested this against actual hospital constraints. To keep throughput high without crashing local servers, they use logarithmic batching. The backend uses a fast API inference server hosted on the Render cloud, but for patient data, it relies on a local SQLite database to maintain the strict audit trails demanded by IVIMA, the Colombian regulatory body. They even optimized it for strict GPU memory limits, maxing out effective batch sizes at 24 on standard NVIDIA T4 GPUs. This is AI engineered for reality, not just the lab. On the front end, clinicians interact with a clean React web interface. It has one absolutely brilliant feature, a real-time GradCam toggle. GradCam provides spatial attribution. It instantly generates a heat map right over the CT slice, showing the doctor exactly where the AI is looking to make its decision. Because it's computed so efficiently, the radiologist can visually verify the AI's logic on the fly without slowing down the system latency. It's turning a traditional AI black box into a completely transparent, collaborative tool. Finally, we wrap up with Section 6, Building Trustworthy Clinical AI. Let's talk about our current limitations and the future vision. The researchers are refreshingly intellectually honest here about their current limitations. Right now, the system handles binary classification, nodule or normal. Future work will expand this to full multi-class malignancy prediction. Also, that continuous learning loop we talked about, it carries a risk called catastrophic forgetting, where learning new data makes the model forget old data. They plan to tackle this by integrating elastic weight consolidation, or EWC. And while the stress tests on distribution shifts look fantastic, the ultimate goal is prospective, real-world validation across multiple hospitals, completely compliant with strict tripod reporting guidelines. Which brings us to our final takeaway. The OncoTriage architecture is proof that the goal of clinical AI simply cannot just be getting a high score on a leaderboard. It absolutely has to be trustworthy decision-making under uncertainty. By blending EfficientNet B4 with Monte Carlo dropout and wrapping it in an intelligent queuing system, we are taking a massive step towards safe, genuinely deployable healthcare AI. It really leaves us with a provocative question. What happens to the future of medicine when we stop demanding that our machines be perfectly certain all the time, and instead engineer them to be perfectly honest about exactly what they do not know?